Okay, so welcome back to this next video in which we are discussing product groups. Okay, right. So in the previous video what we discussed was the construction of the product group of an arbitrary group capital G with another group capital G prime. Okay, and these two groups don't need to be related to one another in the slightest, okay, so they're just two arbitrary groups. And we've discussed that the way that you actually construct this is that you firstly construct the set, which consists of all ordered pairs of elements from these two groups. So all things of the form little g prime, where little g is an element of the first group, capital G, and little g prime is an element of the second group, capital G prime. So the first thing that you do, the thing that you start off with, is constructing this set containing all combinations of one element from the first group, capital G, and another element from the second group, capital G prime. Okay, so that's the set that is going to form our product group G cross G prime. Okay, so it's just the Cartesian product of the set that underlies G with the set that underlies G prime. Now to turn that into a group, what we need is a composition law defined on this set of ordered pairs. Okay, so if you take two arbitrary ordered pairs, A prime and B prime, and you want to compose them together, the way that we defined this is that you do it component-wise. So you compose A with B, and A and B are both elements of the original group capital G, so you can compose them together in the group capital G. Okay, then what you do is you take A prime and B prime, which are both elements of capital G prime, and you compose them together in the group capital G prime. Okay, and this gives you a new ordered pair of an element from capital G with an element from capital G prime, and that ordered pair is going to be the answer to what A prime composed with B prime is. That's how I'm going to define composition on this new product group that I'm trying to create. Okay, so in the previous video what we did is we showed that with this new definition for composition, this set does actually become a group. So this composition law does actually form a group, so that's excellent. It does obey the axioms of group theory. Okay, so what I now want to do in this video is I firstly want to give you an interpretation as to what we are actually doing here. What does it mean to take the product group of one group with another group? Okay, and what I mean by that is, throughout this playlist on group theory, we've seen that it's been very helpful to often think of the elements of a group as representing set permutations of some set, and then the composition law on the group as representing the composition of the set permutations that those symbols represent. That's a very nice way to get associativity, which without this is a very, very tricky property to actually get. Okay, so what I now want to investigate is if we can think of the elements of the group capital G as representing set permutations of some set, and we can think of the elements of capital G prime as representing the set permutations of some set, what can we interpret the product group of G and G prime as, basically? Okay, and it has a very nice interpretation, so we're going to look at that. Then what we'll do is we'll have a look at an example of actually taking a product group of two groups, and we'll illustrate how we can interpret the taking of the product group of those two groups, i.e. in terms of set permutations. Okay, so firstly then let's discuss the interpretation of the product group of G with G prime in general then. Okay, so I'll get a new piece of paper then for this. Okay, so firstly, let's just do the background, the setup for this then. So let's say that the group capital G, okay, let's say we can view the elements of this group capital G as representing set permutations of some set, and I will call this set capital S, and then I'll subscript it G. So quite simply, the capital S is for set, and then I've subscripted it capital G to remind us that this is the set which we're going to think of the elements of capital G as representing set permutations of. Okay, so the elements of capital G then can be thought of as representing set permutations of this set SG onto itself. Okay, So these are bijective mappings from the set to itself, basically. Okay, so I'll just highlight all of this up in blue here. Now similarly, for the group capital G prime, the other one that we're going to use to construct the product group, let's say we can think of the elements of capital G prime as representing set permutations of some set also, and we'll call this set capital S again for set, and we'll subscript it G prime this time, so that we remember that it's relating to the group capital G prime. Okay, so all of the elements of capital G prime can be viewed as representing set permutations of this set SG prime. Okay, and I'll highlight this one up in turquoise here. Okay, so our great question now is, can we interpret the elements of the product group of G cross G prime as representing set permutations of anything? What can we interpret this as actually meaning? Okay, in terms of these sets SG and SG prime, and we can interpret it as meaning something. Okay, so to motivate this, let's have a look at an arbitrary element from the product group of G with G prime. So an arbitrary element of this product group will look something like so. Let's say little g with little g prime, like so, where little g is some element of the group capital G, and little g prime is some element of the group capital G prime. Okay, so I'll highlight up little g in blue because it's from the group capital G, and I'll highlight little g prime up in turquoise because it's from the group capital G prime. Okay, so what then can we view this ordered pair from our product group as actually representing? Well, basically what we can imagine doing is unioning together the set SG with the set SG prime here, okay, to create a bigger set. Okay, so let me just draw a picture of this. So we're creating a new set which will be made out of the union of the set SG with the set SG prime. Okay, so let's say this is the set SG and this is the set SG prime, and we have now unioned them together. Okay, and we're imagining that both of these sets contain completely different symbols, so that there's no symbol that's in both of them. Okay, so we're imagining that the intersection of them is completely empty. If the intersection wasn't empty, then just change one of the symbols so that you don't have duplicate symbols in both of these. Okay, they need to be completely different sets. Okay, that's easy to do. It's nothing to do with the actual group after all. You can change the symbols of the set as long as you don't change the set permutations, then it's fine. Okay, so I will highlight up this set in blue here, and I'll highlight up this subset of our new set in turquoise here. Okay, so if we now want to consider our element of the product group of G with G prime here, so we've got our little g prime element here, we can view it as representing a set permutation of our new set SG unioned with SG prime. Okay, and the way that we can quite simply interpret this is we can say, okay, I want to make a set permutation of this set onto itself, so I'll draw another copy of the set here. So here's another copy of our set. There's the SG portion, and here's the SG prime portion. Okay, and I'll colour them in once again. So we'll have the SG portion in blue here, and we'll have the SG prime portion in turquoise. And hopefully you might be able to guess how I'm going to define the set permutation that we'll associate with this element. Okay, quite simply, I can use the fact that little g represents the set permutation of SG. Okay, and I can say, okay, all of these elements in this subset of this new set in red here, and I think I might even outline the entire set in red here. So this is our entire set that we're now imagining set permutations of, and it contains these two important subsets. Okay, so I'm going to map all of the elements of the blue subset here, the SG subset of our red set, onto what they'd be mapped onto by this element little g, and of course little g will just map them onto elements of SG here. Okay, so quite simply I'm going to map all of these elements onto elements in the set SG as they would be mapped under this element little g. Okay, and I can do that because little g is an element of capital G, and I said that I can view the elements of capital G as representing set permutations of this set SG. Okay, then what I can do is I obviously now need to know where am I going to send the rest of these symbols, the symbols in the turquoise subset SG prime here, and quite simply I'll send them onto where the element little g prime would send them. Okay, because little g prime is an element of capital G prime, and of course we've already said that all of the elements of capital G prime are associated with set permutations of this set SG prime. Okay, and together those will actually create a set permutation of the entire red set, basically. Every element on here will be sent onto an element here, okay, and because both of these are onto, that will mean that this is entirely onto, and because they're both injective, that will mean that this is injective as well. Okay, so I'm using both of the elements then to create this new set permutation of the union of SG with SG prime. Okay, right, so that's how I can interpret all of the elements of this product group of G with G prime, basically how I can interpret them as being set permutations of some set. Okay, if you can interpret, or rather if you have an interpretation of the two initial sets, G and G prime, as representing set permutations of some sets. Okay, right. Now, of course, what I need to show you, or at least give you an argument for, is why this then is in agreement with the composition, because this is all rather lovely. I've now shown you how you can think of all the elements of the product group as representing set permutations of some sets, specifically this union of SG with SG prime. But of course, the other part is that we want the composition law on the group to represent the composition of those set permutations that the elements represent. Okay, so what I want to explain to you is why, if I take two arbitrary elements, A prime, and let's say B prime, from my product group, why, when I compose them together in my composition table according to the definition that I've created you, why that corresponds to the composition of the set permutations that I have now shown you how to associate with each of these elements. Okay, so let's say we were thinking about how we would define composition of these two elements if we wanted it to represent composition of the set permutations that I've just shown you that we can associate with the elements of the product group. Okay, so remember, when you have two elements of a group composed like this, the way we always interpret it is do this one first, do the set permutation associated with this one first, then do the set permutation associated with this one. The net set permutation is then the answer. Okay, so let's draw this out. Okay, so I'll need 3 copies of my new set SG unioned SG prime. Okay, so here is my new set. I've now twisted it over. Okay, and I'll color code it in a moment. So here is another copy of it here. So all of these are this set SG unioned with SG prime. I'm just drawing them out now so that I've got them ready. Okay, so I'll outline them in red. And then, of course, I've split them in two because those are the two major parts, SG and SG prime. So I'll have, once again, SG outlined in blue here in all 3 diagrams. And then I'll have SG prime, the other important subset of the SG unioned SG prime set, in turquoise here on all 3 pictures. Okay, right, so now let's think about what composition of these composition of these elements would be if we wanted to define it in terms of composition of these set permutations that I've now associated with each element of the product group. Okay, so the set permutation B prime then first. Okay, so this will mean the set permutation associated with B on this set SG, so here this is SG going to SG under this element little b, and of course the subset SG prime, we will map this according to the set permutation associated with B prime. Okay, so that now is the set permutation of the entire set associated with this element B prime, basically. Okay, I'll just complete this picture by putting in SG prime here. Then what we want to do is want to compose this set permutation that we have, which is the set permutation associated with B prime, with the set permutation associated with A prime. Now the set permutation associated with A prime will map the set SG onto, again, SG here, according to the element little a, and it will map the subset of SG prime onto, again, the SG prime subset here, according to the element little a prime. Okay, so now if I want to actually work out what is the net set permutation here, what would it actually be equal to? Well, the net set permutation for this subset SG here, okay, so going from here to here, what's that actually going to be equal to? Well, it's going to be the same as the set permutation associated with A composed with B, where this composition is composition in the original group capital G, okay, because remember, these are the set permutations associated with the elements according to this association of set permutations up here. Okay, and we know that composition of elements from the group capital G represents the composition of the set permutations that they represent of this set SG. So if we're just composing, if we're firstly doing the set permutation associated with B and then doing the set permutation associated with A, the answer then of course will be the set permutation associated with A composed with B. Okay, then for SG prime the exact same thing holds true. Overall, what we're going to map this subset SG prime onto is the same as the set permutation associated with A prime composed with B prime, where this composition is in the second group, capital G prime. Okay, and again, that's because we've already said the initial assumption was that we had this association of the elements of G prime with set permutations of SG prime, and that the composition law on this group G prime represented the composition of the set permutations that the symbols represent. Okay, so overall then, what is this net set permutation here? Well, it's going to be the set permutation A composed with B, because this first entry in the ordered pair tells us where the subset SG is going to be mapped onto, and we know it's going to be mapped onto A composed with B, and I'll just colour in that composition symbol in blue. Okay, and then the second entry here is going to be A prime composed with B prime, because this is the symbol from G prime that represents the net set permutation of this subset SG prime. Okay, so again I'll colour that in turquoise. Okay, so that is why this composition law that I've just defined actually does respect the composition of the set permutations that I've shown you that we can associate with these elements of the product group. Okay, so that now is a nice interpretation of how we can interpret the elements of a product group. Okay, so I'll have a break here, and in the next video what we'll do is have a look at an example of this and we'll see all of this in action.